Imagine waking up one day to find that everything you know, everything you've ever touched, seen, or felt, is not as three-dimensional as it seems. What if the universe itself, with its vast galaxies and cosmic wonders, is nothing more than a hologram? It sounds like the premise of a science fiction tale, but this theory is rooted in serious physics and could redefine our understanding of reality. The genesis of the holographic principle. The holographic principle was born out of one of physics' most mind-bending puzzles, black holes. In the 1970s, physicist Jacob Bekenstein made a groundbreaking discovery while studying black holes. He proposed that the information about all the matter consumed by a black hole isn't lost within its enigmatic interior, but is instead stored on its event horizon, the boundary that marks the point of no return. This ran counter to prior assumptions and set the stage for a paradigm shift. The revelation that the surface area, not the volume, of a black hole dictates the amount of information it can contain posed a deep question. Could this concept apply to the universe itself? Enter theoretical physicist Leonard Susskind, who, along with the insights of Gerard T. Hooft, formulated the holographic principle in the 1990s. This principle suggests that all the information within a three-dimensional region of space can be described by a two-dimensional surface that surrounds it. In essence, our reality might be akin to a 3D projection from data encoded on a 2D cosmic screen. Black holes and the paradox that started it all. At the heart of the holographic principle lies one of the greatest conundrums of modern physics, the black hole information paradox. When Stephen Hawking discovered in 1974 that black holes emit what is now known as Hawking radiation, it meant that black holes could eventually evaporate and disappear. This raised a problem. If a black hole vanishes, what happens to the information about the matter it consumed? According to quantum mechanics, information cannot be lost, but how could that be reconciled with the disappearance of a black hole? Bekenstein and Susskind's work suggested that the information isn't lost, but encoded on the surface of the black hole. This idea defied classical intuitions about space and volume, hinting that the surface area of an object could encapsulate all its informational content. Reality on a cosmic canvas. The holographic principle implies that the universe we perceive might be an elaborate projection. Picture an old-school film reel, where a flat strip of film encodes information that, when illuminated, produces a three-dimensional moving picture. The cosmic analogy is that the 3D universe, with its stars, planets, and black holes, might similarly be projected from data stored on a 2D surface, the boundary of the universe itself, or a distant cosmic plane. What lends credence to this theory is its alignment with quantum field theory and the laws governing black holes. In the early 2000s, Juan Maldacena made a significant breakthrough by developing a model known as the anti-de Sitter conformal field theory, ADS, CFT, correspondence. This mathematical framework provided compelling evidence that certain theories of gravity in higher dimensional space are equivalent to quantum field theories without gravity in lower dimensions. In simpler terms, what happens in a three-dimensional gravitational world can be described perfectly by a two-dimensional world without gravity. The universe's cosmic hard drive. But here's where it gets even more fascinating. The holographic model suggests that every particle, every quantum fluctuation, is encoded on this vast 2D boundary like data on a computer's hard drive. The implications are profound. The fabric of reality may not be as fundamental as it appears. If the holographic principle holds, then everything we know, down to subatomic particles, arises from this encoded data. Some physicists even speculate that this principle could bridge the rift between quantum mechanics and general relativity, two pillars of modern physics that notoriously refuse to play well together. The potential for a unified theory, a theory of everything, hinges on whether we can confirm that the universe operates on this holographic blueprint. Cracking the code, where are we now? The holographic principle isn't just an abstract thought experiment, It's being tested in the laboratories of theoretical and experimental physics. Recent studies involving quantum entanglement, a phenomenon Einstein famously dubbed spooky action at a distance, have bolstered interest in the holographic nature of reality. Researchers have found that entanglement might be responsible for the very fabric of space-time, stitching together disparate points of space. In 2022, a significant experiment conducted using quantum computing technology demonstrated a simplified model of a holographic universe. Physicists simulated a two-dimensional quantum system and successfully mapped it to a three-dimensional space, mirroring the holographic relationship posited by Maldacena. Though still rudimentary, such advances push us closer to validating whether our universe truly operates as a grand projection. What if we prove it? The philosophical and existential implications are staggering. If our reality is indeed a hologram, then questions arise about what lies beyond the surface, projecting our existence. Is there a deeper, more fundamental layer of reality? Would proving this principle imply that the universe is deterministic, controlled by the encoded data at its boundaries, or is there still room for unpredictability? The holographic principle beckons us to rethink what we know about space, time, and existence itself. Are we beings of flesh and blood, or are we part of an extraordinarily complex cosmic illusion? For now, the evidence is still being collected, the equations refined, and the theories tested. But one thing is certain: the holographic principle holds the promise of revolutionizing our understanding of the universe and our place within it.